Here we're going to solve the associated system and an initial value problem for the example problem, that damped harmonic oscillator that we did in the previous video. You don't need to write this down. I just copied this from our last video so I could reference it more easily in this video. So start with an example, and I want you to solve this system of differential equations. dy dt is equal to 0, 1, -10, -7 times y. And what you'll notice is that this is the exact same system of differential equations that reflects this second order differential equation. If you convert this second order differential equation to a system of differential equations, you will indeed get this system. Now, hopefully our system will have the same solution. So I want you to get some chapter 3 practice. Maybe this will have repeated real roots. Maybe this will have distinct real roots for the characteristic polynomial. Maybe this will have complex ones. Pause the video right now. Solve this system using techniques of chapter 3. And what you did when you did that, you should get that your two eigenvalues are -5 and -2. Your two eigenvectors are going to be respectively something along the lines of 1, -5 and 1, -2. Again, it could be any constant multiple of these vectors, and that should give you to your general solution, y of t, was something like k1 e to the -5t times the vector 1, -5, plus k2 e to the -2t times the eigenvector 1, -2. And again, it could be any constant multiple, which is not a problem because k1 and k2 are any real number. And you can see that this is exactly the same solution. Right? These are exactly the same. One is just written in vector form, and one is written in scalar form up here. Remember, vector is, multiple entries. Scalar is when, there's just one entry or one output. This is a vector valued function. These are scalar valued functions. But you can see we got the same thing. So again, guessing, this method where we just guess an exponential thing, is going to be the same as solving it with our techniques of chapter 3. And of course, we would expect not to get multiple solutions because we know that under certain nice conditions, and this is a very nice differential equation, under certain nice conditions, we are guaranteed uniqueness of solutions. So if we found a separate solution that was different from the first solution, that solution would not be unique anymore, and we'd have a serious problem. Okay, so quick little summary. When is which form better? This up here is our scalar form. And a lot of times this is quicker to get to. We can use shortcuts. We don't have to worry about taking extra derivatives, or we can if we want to. But again, let's just focus even just on this solution for y. We don't always need the v at all. And it really will be quicker. We can use that shortcut. Everything will be fine and dandy. Over here, right, is our vector form of our solution. And this is better for qualitative analysis. We're going to really show why later in this section. Why is this vector form so useful for qualitative analysis? It's the most exciting part of the section for me. It's just, we get to say some really powerful things and get to use the knowledge that we have instead of just plugging things into formulas and seeing what happens. It's really cool. It's exciting, but we're not there yet. I have to be patient. Okay, we solved the associated system. Now, again, I want to briefly show you how to solve initial value problems. You probably already know what to do, but let's look at initial value problem for the last example. Suppose I told you that y of 0 equals 2 and y prime of 0 equals -13 for the previous equation. The previous differential equation, right? The damped harmonic oscillator, the only example that we've worked at this entire video section, this entire section. All right, well, what do? You just plug in and solve a system of equations. I should have copied this again because we're going to need it. right? So again, we know this is what y and this is what v are. So if we just grab it and move it to the next page so we have it in the right spot. Excellent. We just plug in. We know y of 0 needs to be 2. So when we plug in 2 to this first equation, when we plug in 0, we should have it equal 2. Plug in 0, this just becomes k1. Plug in 0, this just becomes k2. And when we plug in y prime of 0, we'll plug that into the derivative, which you could either calculate yourself or we already found it. And that needs to be negative 13. Plug in 0 here, we get negative 5k1. Plug in 0 here, we get minus 2k2. We have a systems of equations. You could solve it a couple different ways. I really like just doubling everything here and then adding the equations together. Because then what we get is negative 9 equals negative 3k1 plus no k2s. And we'll get that k1 has to be 3. Similarly, if k1 is equal to 3, we know k1 plus k2 has to be 2. So k1 is 3, k2 has to be negative 1. You could double check. I always like to double check into the second one, right? If k1's 3, this is negative 15. This is negative 1. Negative 15 plus 2, negative 13. We could get our particular solution. Is k1, which is 3, e to the negative 5t, plus k2 is minus 1, e to the negative 2t. That's how you solve initial value problems. You just plug in initial conditions into your original equation, your solution and its derivative, and then you solve the system. That's how we solve initial value problems. Of course, you're going to have to find the general solution first. But that's basically it for this video. Let me know if you have any questions. And in the next video, we are going to say, well, does guessing still work if it's not as nice of a situation? Here we guessed and it was nice because we just got distinct real roots. What happens if the roots are complex? The answer is good news. But you're going to have to wait until the next video to actually get that answer. So bye-bye.